All right, so the first of our topics that we have to talk about is the sort of rudimentary phase diagram. It's a graphical way of representing the variable dependencies of the different phases of matter within a substance. So we're going to have basically our two axes. We're going to have one axis that's pressure and one that's temp. And between these, what we're going to see is a bit of predictability. So what I'm going to do is draw the generic one for water. This is actually in your book. It's not really drawn to scale, but we'll forgive a little bit of liberties on that respect here. So you get this diagram for a normal substance. It looks a little bit like a Y. It doesn't really tell you a whole lot. But when you start having a little common sense about it, you can sort of figure out where in this diagram certain phases should be. If you start cooling things down, no matter what we're talking about, if we're moving in temperature down on the scale, we're going towards a solid phase. Think about water. You cool it down, it freezes. So this is the solid phase in the far left side of this. And it also is where you see, for the most part, as pressure increases, you'll compress the molecules down to a solid. Now, water is a little bit exceptional in that this line slopes off to the left. So that will change up in ways it doesn't for other substances. We'll talk about comparative ones a little later. In the middle is the middle of the phases. This is the liquid phase. And at the far right, as you heat things up, this is the gas phase. So the phases should be relatively obvious. Hopefully they're relatively clear here as to what's going on. But what else is happening at the same time is these transitions. Now, there are a couple of other points on here we want to talk about. First, when we talk about boiling point and melting point, those technically are not correct terms. Those terms are applicable only at a given pressure. And here's what I mean by that. If we basically take a mark here somewhere and say this is 1 atmosphere, well, then as we go across that, this point on the solid to liquid border would be the melting point, or the so-called normal melting point, since we're usually around 1 atmospheric pressure in nature. And this would be the so-called normal boiling point. Now, at least with the boiling point, we talked about this in the liquids chapter, the intermolecular forces chapter, the vapor pressure has to become equal to atmospheric pressure for a liquid to boil completely to a gas. That's where vaporization happens, is when vapor pressure is equal to atmospheric pressure. Well, if atmospheric pressure changes significantly, then what happens to the boiling point temperature? It also changes along with it. So what we're going to see is that's a variable. Realistically, this entire area is boiling. Anywhere along that, if the temperature and pressure are on that line or that curve, the liquid will be converted to a gas. By the same mindset over here, this is melting or freezing, depending on which direction we're going in. Again, not as pressure dependent. Solids and liquids are less compressible, but there's still some. So it will change somewhat if you're going in between. Down here, which for water is relatively small, the solid to gas transition is direct, is sublimation. Now, along with that, we got one additional piece we have to talk about, which is this point in the middle. You'll notice that the lines all intersect here at one point. This is what we call a triple point. And this is the point where all three phases coexist in an equilibrium with each other. Now, we haven't talked about equilibrium yet, but basically at 0 degrees C, for instance, the solid and liquid will interconvert indefinitely. As long as you don't go hotter, it won't all melt. As long as you don't go colder, it won't all freeze. The same for 100 degrees C. As long as you have something containing it, you'll see condensation and vaporization happening simultaneously for the boiling of water. But as you go hotter, of course, it will go completely to steam. As you go colder, it will condense completely to liquid, and then colder than that, condense completely to solid. The triple point is the place in pressure and temperature where technically all three of them exist in equilibrium, which is a little bit difficult to fathom. It's slightly above 0 degrees C. It's actually only about 0.01. So this is 0.01 degrees C. So, right on the line of being basically the freezing point. But the pressure is very low at this point. Here we're talking about a little over 4 atmospheres, 4.3, millimeters of mercury. So we're talking about a very, very low pressure and a very, relatively low temperature where all three of those phases can coexist. Now, as far as the shape of this and its particularities to water, we'll do some comparison stuff a little bit later. But I want you to see where the pieces are. Every phase diagram, at least the basic ones that we're going to deal with, they're all, for instance, a pressure, temperature. We call them phase diagrams. The earth scientists tend to just call them PT diagrams, for pressure, temperature, for other reasons. Essentially, there'll be some point where the phases will meet, a triple point. It may be something simple. Here it's conditions that are relatively unique, that low pressure in nature. You wouldn't see this happen, but it does happen in a lab relatively easily. And then the three phases will always be basically where you see them here. The solid will be the place where you have the lowest temperature, and generally where the pressure increases, you head towards the solid. Water's a little weird in that respect. The gas is the other extreme. In the middle is the liquid. Now we'll look at some more complex ones as we go along, but this is the basics that they'll all have. The more complex ones generally have something else going on, because there are only three phases of matter. What else could be there? Well, that what else is something like a diamond, for instance. It's a different solid phase for carbon. Converting graphite to diamond, and I'll put a phase diagram up for that before we finish this lecture, is actually a little bit more complicated because that's technically not a physical process. Technically, there are chemical bonds being formed and broken in that weren't there before, or were formed that weren't there before, or were broken that were there before. That doesn't happen for this. H2O, H2O, H2O. We don't see anything new forming here during the process. So that's why the earth scientists use PT diagrams, because rather than to call it a phase diagrams, because occasionally there are cases where you're not just talking about physical transformations, you're also talking about chemical ones. We won't go into that in detail in this course, but if you're headed down the environmental engineering or geosciences or geology routes, that's going to be much more relevant to you. Okay, now we're going to look at sort of a compare and contrast here. I redrew the one for water. Again, the solid, liquid, and gas phases. And this, the triple point, is at a low temperature. This is a little bit above 0 degrees C and a little bit over 4 millimeters of mercury. So very much lower than we would normally be dealing with. On that scale, and again, these are exaggerated. Your book does the same thing. Your normal boiling point would be, about 30 feet above this on the scale. But essentially, somewhere along here, you'll see that would be the pressure you're at, and your normal melting and boiling points would be there. All right. So what I'm going to do is put up the one for carbon dioxide now, and you'll see it actually doesn't look quite the same. It's laid out a little differently. What you'll see your book does is they put a little jagged thing here to indicate that the scale is really blown out. And what you'll see up front, you'll notice first thing is that your transition between solid and liquid looks a little different. You notice it slopes off in a different direction. Now that's really important here, because if you look here, like around the freezing point of water, what you're going to see is that if you increase the pressure, you're going to head towards the liquid. If you're here around the freezing point and you increase the pressure, you're going to end up going into the solid realm. So you have a preference here strongly for being a solid. And that's important for later, and this should have the same jagged in it. For our purposes, we deal with this normally as dry ice. Carbon dioxide is, in its solid form, considered to be dry ice. One of the reasons it's called that is it sublimes, doesn't leave a liquid. Well, its sublimation point, its deposition point that it's made at 1 atmosphere here is minus 78 degrees C. You'll see this as a common lab temperature because it's easy to make. We just get a pressure container, we run CO2 into it, we get dry ice to play with. It's easy to cool reactions to that temperature, etc. Your triple point here, you'll notice, is well above that, whereas here it was very far below 1 atmosphere. Here it's actually considerably far above it. It's actually, and the scale is a little off, it's actually a little over 5 atmospheres. It's about 5.2 atmospheres. So we're talking about a good amount of pressure here to make all three phases coexist. We're still talking about low temp though. So the temp here is about minus 56. Yep. Yeah, a little bit over minus 56. Okay. Now, the important thing to notice is if you look at that diagram, though, is other than just the fact that the shape's different, what do you notice is that since there's a very weird liquid phase here, that tells us a little something. Just graphically, we can say without question that there's a difference in these molecules in how they're attracted to each other. They're either forced to be a solid and they stay there, or they stop being a solid the first chance they get and go to the gas phase. So here, a wide liquid phase for water implies, which we already know, it has a lot of intermolecular forces. It has a dipole moment, it has hydrogen bonding, the molecules are attracted to each other. For carbon dioxide, it does not have a dipole moment. The molecule is nonpolar. So the first chance it gets at 1 atmosphere to not be compressed into a solid, it immediately lets go of everything. All what little attraction it had is gone. It's straight into the gas phase. It sublimes rather than going through the liquid. The other point you want to see here, though, is that you'll notice that the liquid to gas transition sort of ends. This is not unique to carbon dioxide, but it is unique in usefulness to carbon dioxide. This is called the critical point. Try that again. Critical. I can spell. Critical point. And this is the point where sort of the liquid to gas behavior sort of blurs a little bit, and you get what's above this point. You get what's called a supercritical fluid, which is behaving partially as a liquid and partially as a gas. They have some really interesting properties because, again, they're not behaving like they should to be either particular phase. So, because this one's at a reasonably attainable pressure and temperature, it's one that people have looked at using in industry. It's used for a couple of different things. One of the uses is to do like decaffeination reactions. So pulling caffeine out of coffee, for instance, one way of doing it is with high pressure carbon dioxide. The benefit there is that when the reaction's over, when the extraction's over, you've pulled out the caffeine, you just open it up to the air, your solvent's gone. So there's no toxic leftovers, there's no solvent disposal to worry about. And yes, I know this is our global warming candidate, but even on an industrial scale, the amount you would use for this would be tiny. So it does have some uses. It's not something that's really practical in a laboratory sense as far as a small scale lab because of the high pressures involved, but it's still attainable at a reasonable set of pressure and temperatures to be usable industrially. All right, since I mentioned it, I figured I'd show you the worst one here. So this is the phase diagram for carbon. Again, the same axes as always, pressure and temperature, but you're going to notice things are a little different here. First, you can kind of tell you're in trouble when your temperature axis has a label on it that says times 1,000, which means each one of these is 1,000 degrees Kelvin, 2,000 degrees Kelvin, 3,000 degrees Kelvin, and so on. So you know this has to be a pretty intensely energetic process to need that type of scale on it. Second, your pressure axis basically starts down here with multiples of atmospheres at the very bottom of the scale. So we're looking at, basically going up in atmospheres by factors of 10. So we're looking at like 100 atmospheres, 1,000, 10,000, and so on. So for convenience, this is actually an exponential scale. It's pretty intense looking. So what we start to see, though, is as before, if you go hot enough and, at a low enough pressure, you are going to see vapor form. So this is the sort of vapor phase for carbon, is above 4,000 Kelvin, below, about 50,000, roughly, 50,000 atmospheres. I don't know if we deal with that pressure all that often. There is a triple point. It occurs at about 4,500 Kelvin, and it goes up, but you'll notice it branches off a little bit. There is then another point that connects, and we'll talk about what that is later. We'll get to that in just a minute. And what we'll see is that this is the liquid phase. Vapor is the gas phase. And at the top of the scale here, of course, is where we'd all like to be able to find an easy way to do things. This is the diamond. So this is the more ordered phase for carbon. Down here is graphite. This is the stuff that, if you were taking notes with a pencil, that you're using right now. In between, you have all types of other odd things happening. You'll see the diagram occasionally has these dotted lines on it. Because this is actually a chemical transition rather than a physical one, there's sort of places where they overlap. So you'll see that this is graphite and what's called metastable diamond, which means there's not a lot of it yet. This is mostly diamond and partly unstable graphite, and then this is the extreme. We don't need to worry about that. But this is a more complicated diagram. For starters, in case you have the idea, which we talk about when we talk about enthalpy, we'll talk about it again with free energy later, that graphite and diamond are easily interconvertible because they're almost identical in energy. They differ in delta H by only about 3 kilojoules per mole. Okay, that's a glass of warm water. Okay, my coffee is hotter than that. But look at this. 10,000, 100,000 atmospheres of pressure. Now, the big deal here is that that's not such a simple thing to do. It's only in relatively recent times that people have actually been able to do this at all and make synthetic diamonds. The process that makes them in the Earth's core and shoots them up through the surface doesn't happen anymore. So there are very few places on Earth where natural diamonds actually exist. There are no new sources that are going to happen. And the places where they happened, unfortunately, because of the diamonds themselves, have turned into places where they're almost constant states of warfare. So, in trying to actually make them synthetically, yes, it can be done, but it's still very, very energy intensive. So if you're looking at diamonds, for instance, you're not going to find the synthetic ones being like, $1.50 versus a real one that's a couple of $1,000s. The reality is it takes, a good amount of that amount of money in energy and engineering just to pressurize graphite enough at a high enough temperature to actually get it to make a diamond synthetically. I'd love to find a way to change that because I'd, love to pay off my bills and not have to work and do this anymore. But it's not a simple process at all. It's a very, very engineering-heavy process to deal with these ridiculously high pressures. So despite the energy picture looking like there's no real difference, the pathway is an extremely difficult one, something we'll talk about in a lot more detail once we get to kinetics in Chapter 15.